This is our 28th lecture on bioorganic chemistry, and today we will discuss about crown ethers. Crown ethers, they are cyclic polyethers in which these oxygen atoms, they are linked by CH2 groups, two methylene groups. They join each other through this oxygen to form these types of cyclic compounds, which are called as cyclic polyethers, and they are popularly called as crown ethers. And their names, they are derived from the shape of the molecule, which looks like a crown. So you can see over here, this is 18-crown-6, and there are total 18 atoms in this cyclic polyethers, and 6 is for the 6 oxygen atoms present in this. So 18-crown-6, and you can see over here in a particular conformation this molecule looks like a crown. That is why these are called as crown ethers. The first crown ether was reported by Ludwig Haas in 1937 when he prepared this 20-membered crown ether. So what he did was he reacted mono-substituted resorcinol derivative, this one, 3,2,2-bromoethoxyphenol. When two molecules of this phenol, substituted phenol, they were reacted in presence of a base, potassium carbonate, in pentane 1-ol as the solvent, then these molecules, they cyclize to give us this type of crown ether. So this was the first report where synthesis of this crown ether was achieved in very low yield. Then one first practical synthesis of these types of cyclic polyether compounds were reported in 1967 by Pedersen, where the crown ether was accidentally synthesized because Pedersen was actually trying to prepare bisphenol A from this bis-2-chloroethyl ether. So when this was condensed with this compound, bis-2-chloroethyl ether was condensed with mono-tetrahydropyranyl catechol, this one, in presence of butanol and sodium hydroxide, then it was likely that bisphenol A will be formed. And when this mono-tetrahydropyranyl protected catechol was contaminated with 10% catechol, so because of this dibenzo-18-crown-6 was also formed as a byproduct during this reaction, and structure of this byproduct was found to be dibenzo-18-crown-6 on the basis of elemental and mass spectroscopic analysis. So Pedersen, he proposed a trivial nomenclature for these types of crown ethers, and according to him, the number and kind of substituents on the polyether rings, they are written, and then total number of atoms in the polyether, they are written first, then the name crown is added, and then the number of oxygen atoms in the polyether ring. So for example, in 18-crown-6 there are total number of atoms in the polyether ring is 18, and then word 18, after 18 word crown is added, and number of oxygen atoms present in 18-crown-6 is 6. So after the crown word 6 is added. So that is how trivial nomenclature of this crown ethers was proposed by Pedersen. And in addition to crown ethers, if these polycyclic ethers, they contain nitrogen or sulfur in addition to the oxygen, then these are called as crown ethers if nitrogen is present, and crown ethers if sulfur is present in addition to oxygen. So these are the structure and names of some of the common crown ethers. So first one is 12 crown 4. So total number of atoms present in this is 12 and 4 are oxygen. So first 12, then word crown is added, and then number of oxygen present. Similarly 15 crown 5 means total number of atoms 15, 5 is the number of oxygen atoms. 18 crown 6 I have already told you. Similarly 21 crown 7, then 24 crown 8, 27 crown 9, 30 crown 10, depending upon the number of total atoms present and number of oxygen atoms present, we give the name to these crown ethers. Similarly, if additional sulfur atoms they are present, then we say 1,4-dithia 12 crown 4. So 1,4-dithia means there are 2 sulfur atoms, and 12 is the total number of atoms, and 4 is the number of hetero-atoms present, 2 oxygens and 2 sulfurs. Similarly here 1 oxygen is replaced by n-propyl group in 12 crown 6, so this will act as a substituent. So n-propyl monoaza 12 crown 4 is the name of this compound. And similarly here 2 methylenes they are substituted by cyclohexyl group. So dicyclohexyl 18 crown 6 is the name of this type of compound. So this is how nomenclature is done in case of crown ethers. Then synthesis of crown ether is very important. The first patent was there in mid 50s by Stewart, Waddan and Borrows. They were trying for the oligomerization of ethylene oxide in presence of aluminium alkyls. So this alkyl may be ethyl or propyl. So when ethylene oxide was reacted in presence of alkyl aluminiums or zinc or magnesium alkyls, they produce 1,4-dioxane and other cyclic materials of crown ethers. So for example, when this reaction was performed, in addition to 1,4-dioxane, 12 crown 4 was formed in small amounts. Then DIBENZO-18-CROWN-6 is very important and used in many applications in analytical chemistry, and this is synthesized in 2 steps. First is 2,2-oxydiethanol is reacted with tosylate chloride. So this will react with the hydroxyl function group, and with the removal of HCl, the hydroxyl group will be converted into a tosylate group in the first step. Then these tosylates, we know that tosylate group is a better leaving group than hydroxyl group. So when this reacts with catechol, then 2 molecules of this and 2 molecules of catechol, they react to give us dibenzo-18-crown-6 in the presence of a strong base like potassium tertiary butoxide. Then synthesis of pyridino 18-crown-6. So pyridine derivative of 18-crown-6 can be synthesized in the presence of a strong base like potassium tert-butaxide. So when this type of diol containing ether linkages 2,2-oxy-base ethane 2,1-dialoxy diethanol is reacted with 1,3-bis bromoethyl benzene. So this will cyclize in presence of this base. This is 1,3-bis dibromoethyl pyridine, not benzene. So there is a mistake here. We need to have nitrogen in this case. So then only we can get pyridino-18-crown-6. So when this pyridine derivative is reacted with this diethanol derivative, we will get pyridino-18-crown-6 as the product. Similarly, diamino 18-crown-6 can be synthesized. This again can be synthesized in two steps. First is carboxylic acid derivative of this ether. So 2,2-ethane 1,2-dial bis oxy diacetyl chloride is reacted with this diamine, and we know that H from here and Cl from here, they will form an amide linkage at both the places. In presence of base, we will get this type of cyclic polyether amide as the product. And when this amide undergoes reduction in presence of lithium aluminum hydride, this will be converted into after this reduction will give us alcohol, and that alcohol will further be converted into this diamino 18-crown-6 in presence of sodium hydroxide and water. So this is how we will get these types of diamino 18-crown-6 compounds from diamido 18-crown-6 on reduction in presence of lithium aluminum hydride. Then di-nor-bornano 18-crown-6 can be synthesized through this combination. So when this diethanol derivative of nor-bornano bisoxy diethanol is reacted with tosyl chloride in pyridine, tosylate of this diethanol will be formed, and here tosylate is a good leaving group. So when this will react with another molecule of diethanol derivative in presence of a strong base, then H from here and the tosylate group from here will be eliminated, and we will get this type of di-nor-bornano 18-crown-6 derivatives as the product. Then applications of these crown ethers. Crown ethers, they are in organic synthesis, they are used as phase transfer catalysts. So for example, in this reaction, which is catalyzed by purple benzene, that is permanganate dissolved in benzene, the orthohydroxyquinones, they are oxidized to orthodiquinones in presence of dicyclohexano 18-crown-6 as phase transfer catalyst. So this is a very important reaction for oxidation of hydroquinones. Then next is the use of 15 membered ring mono-tetrahydropyranyl. So this mono-tetrahydropyranyl derivative of glucose is used as a catalyst for Michael addition of nitropropane to chalcone in presence of sodium tert-butaxide as a base. So this creates a chiral product when 1,2 Michael addition takes place on this carbon-carbon double bond. So alpha beta unsaturated compound chalcone undergoes addition of this nitropropane. A carbanion will be formed that will be added to this, and a chiral compound will be formed under phase transfer conditions. Then crown ethers, they found plenty of applications in analytical chemistry, like they are used in extraction of cations, because cations they can be accommodated in the cavity which is hydrophilic in nature, and outer part of these crown ethers, that is hydrophobic due to non-polar nature of these methylene groups, and because of the presence of lone pair of electrons on these oxygen atoms, the interior of this molecule is hydrophilic in nature. So it can accommodate positively charged cations, so they can be extracted very easily. So crown ethers, they are used for extraction of cations, then separation of different cations, because each crown ether has a cavity which is of a particular size. So 12 crown ether can accommodate different size of cations, whereas 15 crown-6 will 15 or 18 or 21 or 29, depending upon the size of the cavity, can accommodate different sizes of cation. So that is how these different cations, they can be separated based on the size of that cation and size of the cavity of the crown ether. Then as we have seen that these are also used in phase transfer catalysis, and then isotopic separation also they are used. And when they are used in analytical chemistry, they form metal cation complexes which are held by ion-dipole interactions. Dipole is formed because of the presence of these hetero-atoms like oxygen or nitrogen or sulfur. So electronegative heteroatom oxygen of this crown ring, as I have told you, they are oriented inwards in the complex to form this hydrophilic interior cavity, and exterior, as I have already told you, is composed of hydrocarbon, non-polar in nature. That is why this is hydrophobic in nature. Then crown ether metal cation complexes, as I have told you, they are formed. They were described by Cram and Pedersen, and number of types of these complexes can be formed. And these complexes, they may be nesting complexes. Nesting complexes are where the stoichiometric ratio of the crown ether and the metal cation is 1:1, and metal ion fits within the cavity of the polyether ring in this ratio. One crown ether, one molecule of crown ether, one molecule of cation. So one cation, one crown ether, 1:1 ratio. Then perching complex. Perching complex is this type of situation where crown ether cavity is slightly smaller than the cation. So the cavity is slightly smaller than the cation, and cation is just perched above the plane of the ring. So it does not completely go inside the cavity, but some portion of the metal ion remains just above the plane of the ring. So such type of complex is called as perched complex. Then is sandwiched complex. When cation is of very large size and does not fit into the cavity, then two molecules of the crown ether like this, one and one more, they interact with one molecule, one cation, so that cation is sandwiched between these two crown ethers. So such type of complexes, they are called as sandwich complexes. Then club club sandwich complexes is when we are having three crown ethers, they sandwich two metal ions in the stoichiometric ratio of 3:2 like this. So such type of complexes, they are called as club sandwich complexes. The stability of these crown ether cation complex depends on many factors, like what is the size of the crown ether cavity and what is the size of the metal ion, then how many oxygen atoms they are present in the polyether ring, so or how many hetero-atoms, because in addition to oxygen, nitrogen and sulfur may also be present in aza or thia crown ethers. So how many number of oxygen, sulfur or nitrogen atoms they are present in these rings. Then what is the planarity of the crown ether ring vis-a-vis this cation. Then how the placement of oxygen atom is there in the crown ether, whether this is a symmetrical placement or unsymmetrical placement, that will also determine that what will be the stability of the crown ether cation complex. Then how much basic are the oxygen atoms, that substitutions present on the crown ether will also determine that how much is the basicity of the oxygen atom. Then is there any steric hindrance present in the crown ether, that will also determine the stability of this complex. Then tendency of the ion to associate with the solvent, that what are the solvation effects in the complex, that will also determine the stability. Then what is the electrical charge on the ring, that will also determine the stability of these types of complexes. The metal complexation is very important for these crown ethers, and they form a most stable complex with a cation when the ionic radius of the cation is approximately 80 to 90% of the cavity radius for the metal ligand. So depending upon these values, we can determine that which cation will find best inside the ring cavity to form a most stable complex in case of crown ether metal complex. For example, sodium ion will fit best in 15 crown 5 cavity based on the size of sodium atom and size of the cavity of this crown ether. Then potassium ion will fit best in 18 crown 6. Lithium ion will prefer 14 or 12 crown 4 cavity. Then rubidium or cesium, they will fit 21 crown 7 or 24 crown 8 cavity respectively. So these are best fit for these crown ethers because the ionic radius of the cation is approximately 80 to 90% of the cavity radius of these crown ethers. Then these crown ethers, they are also used for HPLC chiral stationary phase. So they have been utilized in resolution of various types of racemic compounds containing a primary amino group. So these are some of the examples which have been used as chiral stationary phases in HPLC. For example, this 22 crown 6 derivative of naphthyl based compound has been used as chiral stationary phase. This is coated on octadecyl silica gel and then used as chiral stationary phase. Similarly, this 18-crown-6 derivatives tetracarboxylic acid is used as chiral stationary phase. Then this 18-crown-6 derivative of phenolic pseudochiral crown ether, which is used as a chiral stationary phase in combination with silica gel. Then is cryptates or cryptands. These are also crown ether like cage compounds, but only difference is they are having an additional strap. So for example, these types of crown ethers, and they are having this additional strap. One additional strap of ethers is present in these types of compounds, and if an additional strand is there or additional strap is there, then instead of crown ether we name those as cryptates or cryptands. So these are three-dimensional, whereas crown ethers, they are two-dimensional, and they are named depending upon number of oxygen atom in each of the nitrogen bond strap which are present. So for example, in this case this is named as 2,2,2 cryptland because there are two oxygen present in this strand containing nitrogen bond strap. So this is how they are named as cryptates or cryptands. So they can be synthesized, and their first synthesis was reported by Nobel laureate Lane when they cyclized these types of diamines with dicarboxylic acid derivatives in presence of sodium hydroxide and water. The first the amide crown ethers, they were formed, which on reduction gave us diamino 18-crown-6, and these diamino 18-crown-6, when they were reacted with another molecule of these carboxylic acid derivatives at very dilute solutions, and additional strand of this ethers was substituted into these diamino crown ethers, and these amides then they were reduced to these types of cryptates or cryptands. Thank you very much.